Welcome Dmitry Gavinsky from NEC Labs nearby on quantum fingerprints that keep secrets.
Thank you. So, as I mentioned in the abstract, it has words, as you see, it has the word quantum in the title. And the price I'm going to charge you for that is basically just, I think, the bracket notation. I on purpose did not try, not trying to go, I mean, just trust me that every kind of quantum thing I'm talking about is efficiently doable. So I on purpose did not want to go into details of constructing quantum circuits. Also, I don't think this is the most interesting part of this work. And also, of course, to make it easier for people who are less familiar with quantum stuff. But yeah, but I am using bracket notation. Anyways, if anything isn't clear, please stop me and ask questions. So first of all, let me introduce the notion, high-level idea. So one of possible views of what we are doing is you can think about it as one-way communication problem. Sometimes it's more common and maybe more natural to view these kind of problems like a fingerprint, these kind of protocols like fingerprint protocols, which you can think about as hashing protocol. Sometimes it's natural to view it as a solution to equality problem in simultaneous message passing model. And maybe I'll mention that a little bit more later. But for now, let's think about one-way communication model. So here what we have, Alice receives X, binary string, Bob receives Y. Alice wants to send Bob a message, single message. And the goal is to have a fingerprint or hashing of X such that Bob would be able, given Y, and given the message, to decide whether X equals Y. Of course, well, I keep repeating the word hashing. It's easy to solve classically. Use any, actually I'm going to write it right here, any two collisions within the hashing family can serve as a classical solution to this problem, trivially. Okay, observe here that what we have is actually the error event or like bad case exactly corresponds to hash collision, okay? Because if X equals Y, answer is always correct in the classical protocol. If it's not, then the only case, I mean, if X is different from Y, then error only occurs if corresponding hashing function has the same value over X and gives the same value, same labeling for X and for Y, which is exactly hash collision. Now let's look at this protocol and ask ourselves this question: how much information is leaking? Okay. In other words, if you have, let's say, somehow Alice and Bob want to solve this problem without letting adversary know too much about X. And here it's quite easy to see that if you have a classical protocol, actually the only way for you to make a classical protocol more reliable is for Alice to tell more about the fingerprint, about the X. And if she tells more about X, it means that she leaks more information. Okay, here we're talking about a situation where there is no shared randomness, right? Because if you assume shared randomness, you can do one-time pad and do whatever you want. So no shared randomness. Just again, maybe some sense more natural to view it in the context of simultaneous message passing. I think one way is good enough to really show all the ideas and all the results. So let's for a while stick to the one-way case. Alice, Bob. Alice speaks to Bob, and that's it. So as I said, only way to make protocol better is to reveal more accurate is to reveal more. So well, just trivial arithmetics here, which says, well, basically leak, we define it, leak as entropy that an eavesdropper, let's say the mutual information between message and X. So this is the amount of information that eavesdropper can get about X. Okay, and it's easy to see that leak is always at least log of 1 over error. So whenever you get a protocol with error epsilon, classical solution, then always such a protocol leaks a certain amount of information. This certain amount is always at least log of 1 over epsilon.
What's probability of Y? What's that over?
Yeah, it says, well, basically think about it as a message, think about it as a partition. Okay, so a partition basically gives you how much, how much, here what I'm trying to say is that kind of size of a typical cell of your partition basically tells you how much information is revealed by the fact that you color your X according to that partition. Okay.
So this Y is a bound variable. It's not the Y necessarily, although it is. I mean, implicitly it is that Bob has. Right?
Oh, right. So yeah, of course, sure. So of course, this is with. Well, yeah, I assume here, I think implicitly some kind of symmetry, that for every X it's about the same. I think actually you probably would like to write here probability with respect to X comma Y.
So uniform. Would that be probability XY, or would that be expectation X log of 1 by probability Y?
Let me think about it. Okay, so okay, let's put it this way. Basically, if you think about, let's think about a typical case. Okay, you have k bits, which means your message partitions space of all possible x's into 2 to the k cells. Okay, now let's think about the best you can do in terms of solving the problem. The best you can do is have 2 to the k arbitrarily equal size cells, right? And you label x according to those cells, which means you leak k bits about the, okay, now you can of course move aside and make some of the cells smaller, some of the cells bigger, which on the one hand tells you that actually entropy of message becomes smaller, which means you leak less about x, so leakage goes down, but also accuracy goes down, right? So again, this basically this is to say that that's what has happened. So the only way. Yeah, so whether x must be inside or outside is it's a good question. I think here I decide, here I define, leak with respect to fixed x. No, it cannot be.
No, it's
doesn't make sense.
Distribution.
It's with respect to uniform distribution.
H of x would be expectation x log of the PA.
Exactly, you're right.
So there's an outside expectation over x.
You're right. It's yeah, you're right. So here it's expectation over x. You're totally right. Sure. Yeah, thanks. So now let me tell you briefly why one of the reasons why we started thinking about this problem. It's just as a kind of side note, but I think it might be interesting. One of the reasons because it points to a very interesting one of big open problems actually in communication complexity. And I think a very interesting one. So one of the not conjectures, but maybe one of the possible hopes that we had when we started to look at this was actually that something like this would not be possible. Okay, and what we were thinking about is just to say something like there's a famous open problem asking whether in any reasonable communication model, let's think about one-way communication, whether it's possible or not get bigger than polynomial separation between quantum and classical communication for a total function. Okay, it's open for quite long. I think most people believe that it's not the case, that it's impossible to get separation bigger than square, I guess. Well, I think it's more open. Maybe you can get something better than square. Even that is not clear how to do. But I think many people believe that more than polynomial you cannot get a gap between quantum and classical complexity for the same problem. Actually, I don't think I ever heard a very convincing, at least it would sound to me as a very convincing argument why. Nevertheless, maybe because there is no good ideas of how we can construct something where that would be the case. So, and we were thinking that maybe one of possible ways to say that communication complexity for total problem is always the same is kind of say that whenever we have a quantum protocol solving a total problem, it must leak information. Okay, so that was a hope. Basically, this work shows that that's not the case because fingerprinting is a solution to a quality problem. Okay, we have a quantum protocol. Actually, let me first say what we did. So anyways, this is what happens classically. And our results are that quantumly we can do better. Okay, so quantumly there is we call it quantum fingerprinting schemes that allows hiding information, what we call hiding, about X beyond the classical bound. Namely, we give two schemes actually, but in this work again, for like make it more easily understandable, at least from a technical point of view, I will only be talking about pure state scheme. So we get a pure state scheme, just so you send a vector, okay, in Hilbert space. A pure state scheme that guarantees error, well, whatever you choose, it can be 1 over poly, but also it leaks only constant amount of bits, okay? As we said before, whenever you get error epsilon, classical protocol would leak log of 1 over epsilon. So under this condition, error less than 1 over poly, any classical protocol would leak omega of log bits, okay? We get O of 1 bit. And then we also show a mixed state scheme that can do even better. It gets you both error and leakage upper bounded by any inverse polynomial. And still, it's the both schemes actually, they use only O of log n qubits for n classical bits. Okay, so quantumly we can do better. And again, so assume that this would not be the case. And probably it would be possible to say, okay, whenever we have, again, a quantum solution for a total problem, then basically it leaks information, okay? And it leaks as much as actually a classical solution would cost. And if that would be the case, it would allow you proof that you cannot get a gap between quantum and classical communication complexity for total functions, simply because leaking information basically means that quantum message has that information which it leaks. And we know that in terms of carrying information, quantum do not give you any advantage. So if you only want to encode some like amount of entropy, some binary string x into a message, then send the message and let recipient of the message read bits of x from the message, you cannot quantumly get any non-trivial gain. Okay, so anyways, this to us this gave like an example of something non-trivial from that point of view. We can do something quantumly for a total problem. I mean, not promise problem. It's a total function, equality function, which still does something impossible classically. In some sense, I guess we were surprised to see this. So also we show, well, as I said, classically you cannot do that. And we also show that our constructions are optimal. So surprisingly, well, maybe I don't know how surprising it is, but again, one of the questions one of the possibilities we thought about would be, it's easy to see that any quantum message must leak at least inverse exponential amount of information, because you can just guess what x is, measure. Of course, this argument must be formalized, but it's quite easy to at least to convince oneself that you cannot reveal 0. You always must reveal at least 1 over x amount of information about x. But actually, we show that any quantum protocol, even mixed state, always reveals 1 over poly. I guess what we actually got is something like 1 over n to power 36 or something. But whatever, I think that can be tightened. We didn't try to. So this is tight from that point of view. You cannot do much better. Okay, so let me now introduce quantum fingerprinting schemes. So they are first considered by Berman, Cliff, Wetros, and de Wolf. And indeed, in their case, again, let me say it one more, uses this keyword, simultaneous message passing, one more time. They use it in the context of simultaneous message passing model. But nevertheless, let me tell you in this context what it does. So they discovered quantum fingerprints. So they demonstrated a way to deterministically map a string x to a quantum state over log n qubits. We denote it by alpha of x, just in this cat notation, such that this just denotes, again, bracket notation, just inner product between vectors, okay, 2 vectors in Hilbert space. So the inner product between 2 fingerprints is small whenever the preimages of fingerprints are different, okay? Small means constant bounded away from 1. Okay, now let me maybe just give you remind you briefly how they used it in simultaneous message passing. So actually their use was very nice. I think that was the second ever shown separation between, exponential separation between quantum and classical communications. The first was separation by Ron Ross in late 90s in a different model, in one-way model, and this was 2001. So it was so again, think about equality problem, and we know that if you have simultaneous message passing regime where Alice and Bob are two players, and now they have another player, referee, and now communication goes like this. Only from Alice to referee and from Bob to referee, there is no communication between them. And now, as before, Alice receives X, Bob receives Y, and they send messages to referee. You know, the alpha of X message from Alice, beta of Y message from Bob. And now referee, the goal of the referee, as you can probably guess, is to answer the underlying communication problem given two messages from Alice and Bob. The communication cost of any protocol is just the sum of lengths of the two messages sent by Alice and Bob. And of course, you can see that this model is at least as demanding as one-way communication, right? Because if you have a solution in simultaneous message passing, if you let Bob and referee kind of play together, then the same protocol can solve the same problem in one-way model. Simply this part comes for free. Okay, so this is a more demanding, in some sense, probably you can say this is the most demanding non-trivial model considered in communication complexity context, in the communication complexity context. And here it is known that the complexity of equality, actually, okay, two things are known. Equality problem, if shared randomness is allowed between the two guys, then equality problem given X and Y to decide whether X equals Y or not. Okay, assume that you choose uniformly at random with probability 50% X and Y are the same, with probability 50% they are random uniformly chosen strings. Okay, so if Alice and Bob use shared randomness, then actually the same protocol I mentioned before using hash function works here, right? Because two guys, they can use hashing of what they did, send hashing to the referee, and the referee says guesses that X equals Y if and only if the hash values are the same. But in order to do that, kind of choosing of hash functions must be synchronized. Okay, to synchronize shared randomness is needed. So if you have shared randomness, it's trivial. It's basically the amount of bits of hash. So it can be, I think, log. Actually, it can be constant if you don't count the amount of shared randomness used. It can be constant, and it uses log n bits of shared randomness. Anyways, but if we don't have that, what happens if we don't have that? If Alice and Bob must act, they cannot have mixed strategies. If their strategies must be local. Then it was shown by, I guess, Newman. I think it was Robo Newman, right? The first to show that the complexity is square root n, like 80s. Yeah, complexity is square root n of equality problem if you do not allow shared randomness. Okay. Right, there was a result that showed that whenever you have a randomized solution for any problem without shared randomness, by getting you have another solution at most cost square of the original solution, which gives you deterministic solution. It's easy to see the deterministic solution for equality takes you n, and from that you deduce that also randomized in this model, not also, but from that you deduce that randomized in this model without shared randomness takes you square root n. Okay, so classically without shared randomness, cost of solving equality in SMP, simultaneous message passing, is square root n. Quantumly, this idea works, right? Because this checking whether this is the case given any two quantum vectors, again, trust me, take my word for that if you're not familiar with these facts, given two vectors in Hilbert space, it is doable relatively easily to check whether, to measure this value, to measure inner product between two vectors in a Hilbert space. Okay, so using this approach, we can get, they got a quantum solution for equality problem. Okay, with constant error, any constant, and quantum state over log n qubits, which means complexity of quantum solution was log n, which gave them exponential separation between.
So in the one-way version of this is easy classically.
Precisely.
You can do exactly.
That's why in order to meaningfully talk about the original regime of fingerprints, you really need simultaneous message passing. Okay. In this case, again, we have, even in the paper, we have a comment about this view as SMP, in the context of SMP model. But actually, what we are doing, I think it makes sense in the one way, because we're talking about different criteria, and we do show kind of something unconditionally impossible in one way. But yeah, their context was actually This, and actually I heard from the authors that actually they first came up with construction before that year, and it was they knew that they have this construction, as they didn't really know what to do about it. And then later, one of them came up with the idea of where it can be applied. Okay, so yeah, so actually to show that this quantum original idea of quantum fingerprints, to show that it does something non-trivial, you really need the SMP model. Okay, and by the way, but note that this in this case, and yeah, I think another comment is in place here, that the problem is total problem. Okay, so we do get a unconditional separation between, like, for total function, a problem where quantum algorithm is exponentially more efficient than classical. The only kind of drawback of this thing is you don't allow mixed strategies, okay? Because what does it mean for two guys to not share randomness? It means that you don't allow mixed strategies, okay? So of course we are the conjecture that it's not possible to get for any total functions more than polynomial separation. We're talking about mixed strategies, okay? For even in the context of SMP with shared randomness. So people conjecture that is the case. Okay. But classically, yeah, you want mixed strategies. In order to for things to be intuitive, you want mixed strategies. You know, like minimax theorems and things like that. You really need, because otherwise, if you really ask the question, what? Because think about it, for example, this way. If you fix input distribution, for example, right, this can be viewed, if you don't allow shared randomness, this is a contradiction to minimax theorem. Because if you don't allow shared randomness, you know, once input distribution is fixed, of course, it's easy to solve it classically, right? Because for any fixed input distribution, you can kind of fix shared randomness and always act with that fixed shared randomness and get polynomial accuracy with classical argument, okay? But nevertheless, we say that to have a solution for any distribution, like distribution-free case, we need exponentially more communication. So like minimax doesn't work, and so forth. So yeah, we're talking usually outside this context. Usually we will mean, of course, we would allow mixed strategies. Okay. So yeah, as I briefly described, this is what they do. You given two well, in this case again, it's one-way model. So just given fingerprint of X. Bob measures it with respect to, just tries actually to measure this value, okay, whether the inner product between, what is written here is basically Bob is checking whether inner product between alpha of X and alpha of Y, he knows Y now, is small or large, okay? And then if the value is small, if the value is large, if the angle is small, then he guesses that X equals Y. If the angle is large, or inner product is small, then he guesses that the values are different. Okay.
That should be alpha X, alpha Y.
No, because the thing is, well, the point is that here you...
alpha X onto this.
Precisely, yeah. He knows Y and he computes alpha of Y and he, yeah. Yeah, and error probability is as before. Whenever X equals Y, Bob would always say they're indeed equal. And if they're different, then he has non-trivial probability, constant probability of catching the difference. Okay, if you want to boost accuracy, repeat it several times, as usual. Okay, so now let me say what the rest of this talk will be. So first of all, I'll talk again. This part is actually common to the original work of about quantum fingerprints and our work. How you one of possible ways to construct quantum fingerprint based on error correcting codes. Then I'll show you that, okay, of course, error correcting codes, you can view them as pseudorandom objects, right? Because if you take a random code, it would be error correcting, okay? So codes in some sense are even more pseudorandom than just error correcting, would give rise to hiding schemes, and then we introduce a new type of codes that are sufficiently pseudorandom and do what we want. So first of all, schemes based on error correcting codes. Maybe I shall reveal you the whole picture here. So the idea is the following. This is a construction, okay? So think about i's as any basis for your Hilbert space, okay? And then you construct a vector. This is just a linear combination of vectors, of the vectors from the basis, and you always sum all the elements from the basis, Okay, but you sum each specific element, you put it either with plus or with minus. Depending on what? Depending on Ci of x, where x is the input for which we are constructing a fingerprint, and C is any error, a binary code for now, okay? So first of all, you can see that actually the number, okay, binary code, polynomially, expansion is polynomial, so the number of basis elements is polynomial, dimension of our Hilbert space is polynomial, which means number of qubits is O of log for now. So in terms of dimensionality, we are doing fine. Now, error probability is 0 whenever x equals y, because of course any vector, well, it has, you know, inner product 1 with itself. It's not a big deal. Now, when x is different from y, the error probability is actually given by this value, which is just squared inner product between fingerprints of two different elements. And it's quite easy to see that this value is directly related. It's just equality. It's not greater, not smaller, just equal to this thing. And now d sub h is just the Hamming distance between two code words. Okay, so there's a direct translation between Hamming distance of corresponding code words between for x and y and the accuracy. Okay, but now observe that the dependency is a little bit funny. In which sense? We do not want code words. This would be a bad case. This would be a bad case when for us, for this context, this would be a bad case when x is different from y, but nevertheless C of x is equal to bitwise negation of C of y. Okay, in terms of coding, in terms of like distance, Hamming distance between code words, this is perfect, right? Because it means that the distance is n. But for this context, is terrible. And basically, why is that terrible? Because as you know, we measure inner product, and inner product between two vectors does not change if you do if you multiply by a constant one of two vectors, right? If you just do a scalar multiplication, okay? What it means, this situation would simply mean that you would have two corresponding fingerprints would look like this. One would be the negation of the other. They would look in different directions, which means the absolute value, I mean, of course, inner product changes, but the absolute value doesn't change. And so this means that we do not want such situation. We want actually, so a good code for us would be a binary code where actually all pairs of different strings have Hamming distance of their encodings close to n-half. Okay, and that is indeed what we expect for a random code, and actually many of explicitly, I mean, actually I think all explicitly all used, at least all known to me. For example, linear codes, they have this property, right? Because this is quite rare. You don't expect this to happen when, you know, two code words, one is exactly the negation of the other, or close to being exactly the negation. I mean, why should they? Moreover, I think in terms of linear, this would immediately mean that there is some z such that C of z is very close to C of x. And x is different from z. Anyways, so we want this, like, kind of, I say this can be viewed as strengthening of the well-known minimum distance condition. We want all the distances to be close to half of the code length.
So you're dividing by m, actually, right? So I mean, it's fine if that distance is m over 4.
Precisely. So we just want it to be not too close to edges. I mean, not too small or not m minus, let's say, little o of 1.
So it's really that times that divided by m is o. So it's o of m over poly n?
No. Oh, I see. You say. Yeah, of course, sure. Is small. Oh no. Let me read what was there. Yes. Right. It's here. I mean m over poly n. Precisely. So all the distances are actually very close to m-half exactly. Right. Thank you. Okay. So now, okay, but as I said, we will need more than that to imply hiding. And let me say At least let me try to give some intuition what is more here. So suppose that an eavesdropper has measured the fingerprint alpha of x and obtained outcome v. Okay, for simplicity, let's assume that measurement was a complete projection, which means simply you fix a basis, a measurement basis. Okay, you take a vector in Hilbert space and you project it to one of your basis elements, and the probability of every outcome is proportional to the inner product squared, okay, between the vector and the corresponding basis state, which means if your original vector is unitary, then the sum of probabilities is indeed 1. So these are indeed probabilities. So we have a projection, good. And so some eavesdropper measured, obtained v. And now here, again, you should probably trust me, but I think it's something easy to believe, that actually once condition upon the outcome v, the conditional distribution of possible preimages x's that gave rise to the fingerprint that has been measured to the given v is actually proportional to this value mu sub v of x, which is just inner product between the given vector v and the fingerprint which we have measured squared, as always, of course. So in other words, here it's a kind of, you can view it as overkill, and it might be interesting to do to ask ourselves whether something much better can be done. And again, our tightness result says that you cannot do much better, but basically what we are going to say, not just that for eavesdropper it's difficult to come up with measurements such that, with good probability every outcome of that measurement or many outcomes of that measurement would give something non-trivial. Actually, we kind of want, in order to guarantee hiding properties, actually want more. We want to say, like, kind of, we allow what you might view as post-selection. Okay, even assume that there is some v such that artificially somehow you condition your universe upon the event that a measurement has given you the outcome v. Nevertheless, even in that picture, still we want not too much to be known to the eavesdropper. Okay, so kind of say here again, say here more. So that even in the post-selection scenario, still eavesdropper cannot learn much. So in a sense, it's again stronger requirement, but and it's somewhat surprising, I must say. I don't completely understand why, but we just proved it, that we do not lose anything significant by doing this overkill. Okay, so if we want to show that the amount of classical information about x that can be accessed via any measurement of fingerprint is small, it is enough to lower bound this value. Okay, we said that probabilities of preimages conditional upon v is proportional to this, so we want to lower bound the remaining entropy. Okay, so we want to say that the conditional entropy is large. Okay, the original entropy of x is n, so if we can show that this entropy is n minus O of 1, then we are done. Then we have proved that even in the post-selection scenario, at most O of 1 bits about n has been leaked to any eavesdropper. Okay? You're right. You have to normalize, but again, I mean, once you assume, I mean, you have to do some calculations. But of course, the highest you can get here depends on how many vectors you have. Okay, and we know how many vectors we have because this is our n. So once we are working in the same scenario, then you're right. This does not, as the way I wrote it, it does not have really to be a probability distribution. So it's kind of like, a unscaled version of entropy. But of course, it's one-to-one corresponding. So it's enough to lower bound this value. But you're right. It's not necessarily a probability distribution, but I think it might be convenient to think about it as that. OK, so now comes the definition that will. So by the way, no, the disk might be viewed as a requirement for a code. OK, why? Because just as I said on the previous slide, a code, there is a direct one-to-one natural mapping between codes and fingerprinting schemes. Okay, so for this thing to be high, It says nothing about quantum information, nothing about fingerprinting, doesn't say anything about whatever. It basically tells it is a requirement for codes. Okay. Now let me maybe give you some try to give you some geometrical intuition about why I think this thing can be viewed as another pseudo-randomness, maybe stronger pseudo-randomness requirement for codes. And it might be interesting to look at the question whether this property can be reinterpreted as something else interesting in the context of coding. Also, it might be interesting to ask whether some of the known codes, because in our case, we didn't care about having some randomness in our construction. So what we are using is, it will be not exactly random linear code, but you can think about it as a random linear code. That's good enough for us, okay? But another question is whether some explicitly constructed code would give us that. It would be interesting if there are some, again, if there is some natural interpretation for this code property of codes outside this context. Okay, so let me tell you why I think that this is a like some kind of uniformity condition maybe upon a code. So first of all, maybe I shall remind you the definition of fingerprinting from a code. So this is the definition I'm talking about. Okay, given a code, we have a vector. Okay, and so look at this definition, and I think you will believe me that basically, especially for a randomly chosen code, if you want kind of geometrical intuition, geometrical view of how code how fingerprints would look corresponding to random code, they would look pretty random. Okay, you would have basically something like that. Randomly choose direction in the vectors in your d-dimensional space, and those directions would correspond to your fingerprints corresponding to the code. Now, good. Now let's choose some v. Okay, choose some v, and the property, the requirement that I mentioned on the next slide, this guy. It basically tells you that whatever v it demands, that whatever v we choose, most of the vectors corresponding to our fingerprints are orthogonal to v. Okay, because what it says is that you don't have too many alpha of x's that would have a very small inner product with v. Okay. Now, from concentration properties, like of higher dimensions, it's of course that's what we expect. Okay, if we choose these guys at random, then indeed for any chosen v, most of randomly chosen vectors will be orthogonal, and this is exactly what is required there, not more, not less. So that's why I think that that's why I mentioned in the beginning that I think it's a natural, in some sense, natural pseudo-randomness requirement for codes. Okay. Now we have a way to construct them. These are we call them quasi-linear codes. Before I define, let me make a general comment. So, of course, if you have a total, not of course, but as you can probably expect, if you would use a random binary code, it would satisfy this condition. Okay, so the pseudo-randomness requirement would be satisfied, but actually that would not be that much of pseudo-randomness requirement because a random, there's nothing pseudo about a totally random binary code. It would be just randomness. And the problem with totally random binary code is efficiency. Okay, now let me say a couple of words about efficiency. We don't need decoding. Okay, as you remember, right, that in order to check whether two code words are the same or not, we just measure inner product. To measure inner product, we don't have to decode or something. So it's only important to be able, given x, compute C of x. That's why, from the point of view of efficiency, we can afford linear codes. We don't care about decoding. But of course, we cannot afford random binary code because just to write it down will take exponential amounts of space. So random binary code.
Why does that matter? I mean, it's just a communication problem.
Exactly, but we say that actually, again, it didn't go into those details, but actually all the quantum steps we do here are efficient. So another way to look on all I'm talking about is cryptographic context. Okay, so everything we are doing is efficiently realizable, and random binary code, of course, would be not. Okay, so but you're right, in communication complexity it wouldn't matter. So a random linear code turns out to be insufficiently random. At least we couldn't prove that a random linear. Yeah, I think actually if you ask me, maybe it's really insufficiently random. My intuition would be. Anyways, we couldn't prove that was a fact. That was a fact. That a random linear code would be good enough to guarantee these properties. Okay. So what we do kind of a mixture between a random code and the random linear code. So we add to random linear code a little bit of a totally random code, but this a little bit is little enough to still remain efficient. That's all we do. So when we call it quasi-linear code, and we define it as follows. It's just XOR, point-wise XOR of two codes. Okay, C1 is arbitrary, a real random binary code. Think about it. Arbitrary code, but it's only on the first R bits. And think about R as being log here. And C2 is a linear code on the rest of bits, almost all the bits. Okay, and we do point-wise XOR. You can easily see this is maybe the most natural way to add randomness to a random linear code, and it indeed turned out to be sufficiently good. And so, of course, it's still efficient. A arbitrary quasi-linear code can be described by polynomial number of bits, and also it's efficiently encodable.
So this first one, C1, is mapping log n bits into
n bits.
So
Into
it's just a
M,
lookup table,
M.
basically.
Exactly. You write table for just exponential. Yeah, first is like you exponentially expand it. First log n bits into m, like say n square. Actually, I think it's even O of n could be what we have, or maybe poly n. I don't quite remember what is m. I think it depends on what parameters we want to get. Think about it as yeah, poly n. Then yes, we have just a table m by log n. Sorry, m by 2 to the r. And then another table which describes a linear code. And so it's easy to see. Yeah, another thing to remember, it has nothing to do with shared randomness. It does not require shared randomness, okay? Because this code is, you can think about it as fixed once forever. Simply what I'm going to say is that most of selections would be good, but they do not have to change as as the game goes. Anyways, so it's very easy to see that actually at least the distance requirement is satisfied. It's just counting, almost always just like counting-based method. Which is most demanding, of course, is to see that, well, okay, so minimum distance, even stronger minimum distance requirement where you actually want all the distances to be close to m-half, almost trivially is satisfied by a random construction like this with overwhelmingly high probability. So therefore, a random quasi-linear code can be used to build an efficient quantum fingerprinting scheme. So far, I'm saying nothing about hiding, just fingerprinting. Hiding are a little bit more fancy. It's same property, basically. Okay, for any fixed unit vector v, we show that actually the h sub v0, you can think about it, the same property I talked about before, but scaled, as you correctly pointed out. So it's scaled versus, so it's precisely the entropy of x conditional upon alpha of x having been measured to v, or v0 actually, it must be, okay, v, whatever, v. Yeah, so for any fixed unit vector v, we show that probability with respect to randomly chosen code c, with respect to a code, is very close to 1 of that. I mean, the probability that the value is close to n is very close to 1. Now, and this is technically the most complicated part of our analysis. I mean, it's almost, it's as, I would say, natural and intuitive as it is complicated. Okay, we just go ahead and calculate probabilities. Surprisingly, it took us a lot of space and a lot of concentration bounds. Okay, surprisingly, really surprisingly, I didn't expect it to be that technically complicated. Now, having that, we use a properly chosen epsilon net to say that the probability that there exists any v for which this is not the case is still small. Okay. Again, this is second thing is natural. And also, it's not as technically, the proof is not as technically demanded as the first one. First one was really the most time-consuming part. Okay.
Question about that. So presumably the way for the first part of the analysis goes is you pick this C quasi-linear code
Mm-hmm.
at random, and then probably you say with high probability it has this property and that property and this property, and then you finish the analysis. So what are like these properties?
Okay, so these are the properties, first of all, to say that a random quasi-linear code has the required minimum distance properties, which are easy. And the second is that you remember entropy expression.
Yeah.
So to say that, so first we say whatever v you choose, then the probability with respect to random code. Okay, you want a given code. No, mind. Okay, so for given code, show that for that given code that this probability is, not probability in that case, is just this value for any v.
Oh, wait.
So
hold on.
throw away, yeah, if you want to think about fixed code, just throw away probability.
So in this picture, first B0 is fixed, then C is
So, okay, sorry, by the way, good point. Here, I think we shall have, oh no, it's fine, sorry, yeah, for any V0, yeah, it's fine.
Yeah.
I wanted to add V, no, it's fine.
The second one, you've got the quantifier inside it.
Exactly, precisely. So for any V0, this must be true, and then you kind of multiply this, you do union bound, but of course you cannot do union bound on, uncountable, so that's why we need epsilon net. Okay. Good? So H sub V0 is basically this guy. This guy scaled, the bottom one. Well, again, throw away supermum, just the value, okay? Okay. Oh, that's it. Thank you. Okay. Yeah. So